Okay, so I need you to take this and you're going to fold it in half like this. Okay. And then open it back up and fold the outsides into the middle. Like so. Then take some scissors. There should be plenty of scissors on your table. You might have to get them out of your box. But on the inside, cut along these lines just to the first crease. I know you've done foldables like this like a bazillion times. Just make sure you don't cut too far. You end up cutting the whole thing apart and then it doesn't work at all. Okay, so is Ratey something that you remember doing in Algebra 2? Did she pronounce it Ratey or Ratui? Ratatouille? Okay. I don't know. To me, it's Ratey. I don't know where the ratatouille comes from, but we can call it whatever you want. What are y'all used to calling it? Nothing? It doesn't even look familiar? Oh, okay. I thought y'all did it in Algebra 2 also, so never mind. Y'all have done the pieces. You just may not have done this acronym. We're going to write it out together, too, as soon as you get done cutting. But okay. Then I think Ratey makes more sense, but, actually, I guess it would be Ratty because there's 2 T's in there. That would make it Ratty and not Ratey. I'll wait till everybody gets it cut. And you can use, there's markers and matte pencils in there, too. It's foldable, and you want to use some markers, matte pencils, colored pens, whatever you'd like to do. Alrighty. So, in this first box up here, I will explain to you what the PPD means here in just a minute, but in the same box underneath that, I want you to put all these in capital, R-A-T squared E-Y. So I guess if I actually wrote that out, it would be pronounced Ratty because you got 2 T's in there. But it is an acronym, and that's something that you have not seen before? Yes or no? No, you did not see. Okay. It's an acronym to be able to make sure you got all the pieces that you need to be able to graph your rationals. Now, this is the acronym that really the lesson's about, but we're adding PPD to the top of it. So, and the P goes by itself and then the PD together. That's why I underline them like that. Okay. The ratty part of this is going to come in the rest of these little doors, but on the inside of this one, we're going to talk about the PPD. Okay, so let's open this little door up, and in this first box right here, here's what the P stands for. These are things that you want to check and see if you know before you start. Okay, sorry, I got it right sideways. All right, so for the P, you're looking for, does it have a parent? 2 words, a parent, not a parent like it looks because my handwriting's bad. But does it have a parent? So basically, is this just a transformation of a parent function? And if it was, it would be like f of x equals 1 over x, or f of x equals 1 over x squared. Okay? So if it does have a parent, and it's just a transformation of one of those parent functions, then you don't necessarily have to go through the rest. If the answer is yes, then just do transformations. Okay? So does it have a parent? If the answer is yes, you just do transformations and that's it. And you don't have to really worry about the rest of it because you should know what your parent functions are. It makes it a little bit easier. Now, could you still do the rest? Absolutely. Okay. Then the next thing that isn't actually part of the RATI acronym there is the PD. So what has PD been standing for? Point discontinuity, and it still did. Okay, it still does. So this is point discontinuity. I want to abbreviate because, you know, we can only write so big. point discontinuity. So we are looking for, we should already know what to do, it would be a factor contains X is common to numerator and denominator. Okay. So the factor contains X is common to the numerator and denominator. That's how we find our point discontinuity. That's the first thing that you check, and then you reduce. Finding point discontinuity and domain are the first two things that you do, then you reduce, and then everything else happens. Okay. Everybody good with that? So that's the PPD. And then we start Ratey. Okay. So the R in Ratey stands for roots. And then, is everybody done with the inside of PPD? I don't want to go too fast for you. So roots, what's another word for roots? Zeros. So we're looking for our zeros, basically. And we prefer zeros over x-intercepts because then we don't have to write it as one word pair, right? All right, so then in here, you open that up for your roots. That means we are looking for the x-intercepts. If it is asked like that, your answer is ordered pairs. Right? And then another way to look at it is the zeros of the numerator. And when they're asked for zeros, then you get to put it in the set notation. And a little side note that you need is that these are found after reducing. Because if you do it before you reduce, you're going to get some, you could possibly get some that aren't really intercepts. So R is for roots. That should hopefully make sense to you. What do you think A might be for? Asymptotes, yes. A is for asymptotes. Not asymptotes, but asymptotes. So A is for asymptotes. It's a long word, and I probably didn't give you enough space, so you might have to cram it or put it underneath, but asymptotes. And right now, if the A, it really only counts the vertical ones. We do care about the horizontal ones, but we get to that in a little bit of a different way. So we're looking for just the vertical asymptotes. So when you look for the vertical asymptotes, are we looking at the numerator or the denominator? Denominator. And what has to be true about the factor in the denominator for us to have a vertical asymptote? It's unique to the denominator and contains x, right? It can't be just a whole number. All right, so this one's pretty easy. This is a unique factor containing x in denominator. So all the pieces are things that we've done. This is just reminding you to make sure you look for everything. Okay? So R was for roots or zeros. A is for our asymptotes. Those you've been finding forever, so no big deal. Right? Okay. So T squared stands for 2 because it means two things. And they both start with a T. So open this up. I'm going to write all the way across the two boxes first, and then I'm going to separate things. So do any factors of R or A, which means the numerator and the denominator, right? The roots that you're looking for, or the asymptotes, have an even exponent. So you look for the factors that you have and whether or not they have an even exponent. So for the numerator, if the numerator has an even exponent, like for instance, x minus 3 squared in the numerator. Oops, I guess I need parentheses there. You can't see the square. That's a squared out there. If it's in the numerator, what does that tell me? What did it tell me for a polynomial when it wasn't irrational? When we were graphing them, and if I had x minus 3 squared and it was just in a normal polynomial, what did that mean? It bounced, right? We had a bounce, right? So what's our actual math where bounce is fine, but mathematically, what is that? How does it relate to the axis? If I'm going to bounce, which means it's going to look like this, right? So we can draw it. It can look like this, right? Or it might look like this. Not necessarily just that it's a parabola or anything, but at that point it's going to bounce, right? So how is the function related to the x-axis at that point? What's the word? Starts with the T. Tangent. Good. Okay, so in the numerator, then the T is for tangency that we're looking for. Okay, in the numerator it gives us tangency, which is the bounce that we had looked for before, just like with a polynomial. So in the denominator, so let's say that I have x minus 3 squared in the denominator. First of all, if I have x minus 3 squared in the denominator, what that we've already gone through does that tell me I have? Oh, possibly, depending on what the numerator is. If it was 1 over that, then yeah, it would be a parent function. But of the r and the a, what does that give me? Because see, it says, do any factors have the root, if r or a have an even exponent? The numerator is the root part, right? The denominator is the asymptote part? Yes? Okay. So that means that I have an asymptote at where? X equals 3. Okay. So we're going to draw 2 different little examples of that too. Okay, so here we're talking about our asymptotes. Sorry, my hands are always in the way. And then so the T in the denominator, when you're looking for that even, this stands for togetherness. So if I have a squared in the denominator, then that means that my function is either it's going to come together at the asymptote right there. So let me zoom in a little bit more. So it's either going to look like this or possibly like this. If I do not have a squared in the denominator, then they go in opposite directions. That's what the togetherness part means, because it's giving you the shape of your graph. So if this was just x minus 3 and not x minus 3 squared, I still have an asymptote there, but one would be going up and the other one would be going down. Okay, does that make sense to you? Everybody good? All right. Any questions on the together or on the t squared part? Because you're looking for the t in the numerator and the denominator. Numerator gives you the tangency just like it did for polynomials. And then in the denominator, it gives you the togetherness so you know what's happening at that asymptote. Okay? Let's draw this. Let's draw one more, and then we're going to put a circle with a line through it. Make sure you understand what it isn't also. That is one that's not together. So you can draw that and then kind of just circle with a line through it. Make sure you understand my togetherness. My circle is really bad. Doesn't even look like I tried. I think you get the point. All right, are we all good with that? All right, so roots, asymptotes, together, tangency and togetherness are t squared. E, what do you think E might stand for? Exponents. It's a good guess. It usually stands for exponents, but no, it doesn't here. It stands for end behavior. I am looking for what is the limit of f of x as x approaches positive and negative infinity. Basically, this is where your other asymptotes come in. Your horizontal and your vertical. I'm sorry, your horizontal and your slant, because your vertical ones are taken care of differently. But the end behavior has to do with your horizontal and your slant. Okay. All right, so on the inside here, in the little left box, we'll start with the horizontal asymptote. Okay, we're going to abbreviate a little bit. Those are long words. Or your HA. And then there are three different things that could happen, and the horizontal asymptotes are treated differently. So if the function is top heavy, what's our asymptote? Our horizontal asymptote? None. If it is bottom heavy, y equals 0. Good. So you already know how to do all these things. You just got to make sure that they all happen, and this is going to be a place where they're kind of all put together for you. Okay, and then if they are tied, then what? The ratio of the lead coefficients, right? So y equals, could not come up with a great way to abbreviate all that. So it's the ratio of the lead coefficients of numerator and denominator. Looks like numerator. I was afraid to just put ratio. What kind of ratio you might find. Right, so lead coefficients of numerator and denominator. Right, all 100% review. Then what's the asymptote that's missing? Slant. Okay, so slant asymptote, abbreviated SA. What's another word for slant? Oblique. You have a slant asymptote if the degree of the numerator is what? It has to be greater than the denominator by how much? 1. Okay, is 1 higher than degree of denominator? And then how do you find it? Long division or synthetic division or your short division. So we're just going to put whatever makes sense to you at that point, you are going to divide and ignore remainder. Everybody good with all that? Okay. Last one. Y. What do you think that stands for? Y-intercept. Since the word intercept's long, we'll put a little dash there and we can write underneath it. That's one of the easiest things to do, right? So for the y-intercept, I just substitute 0 in for what? For x, and solve for y. Oops. So when we start off on this, I'm going to, you'll kind of have blanks of stuff you need to fill in before you graph to help lead you through it. But if you are just given a rational function and it says graph it, then you need to make yourself your little acronym. Put down P, PD, and then spell out Ratey, and make sure that you have filled in all those little pieces so you have what you need to be able to graph this. Now, there's still a couple of things that we will talk about to add on to that. All right, but go ahead and glue this in on whatever page that was, and we've got a few minutes. I want to go ahead and do one of those. So let's see. Just need a blank piece of paper. So we're gluing that on what, 76? All right, so then turn to page 77, and let's go through this. On the top, here's page 77. And I want you to write this down. I'm going to start it easy so that we don't have to factor anything. F of x equals x minus 3 over x plus 4 over x plus 2 times x minus 3. And then just down the side of it, we're going to list out, we've got P, PD, R, A, T squared, E, Y. Okay, just space that out. All right, so does this thing have a parent? What do you think? Does it have a parent that you can just transform? No. Okay, so no parent. Does it have point discontinuity? Yes, because I can cancel these out. So my x value is at 3. Then my y value would be 7 over 5. Yeah, okay, so 7/5. What are your roots? My roots just come from the numerator. Okay, -4, so it's just -4. Does it have a vertical asymptote? Yes, x equals what? -2. Okay, so tangency and togetherness. We're looking for, does it have a squared factor in the numerator or denominator? No, so there's no togetherness. Which means at the asymptote, it has to go in opposite directions. That's telling you something when you go to graph it, right? End behavior. Do we have a horizontal asymptote? Okay, they're tied, so what happens when they're tied? It's the ratio, it's 1, so y equals 1. And so then does it have a slant asymptote? No. Okay, and then the y-intercept, I plug in 0 in for x, and I'm going to get 4 over 2, which is 2. So 0, 2. Now, the next thing that you want to do is your sign thing that we did to figure out where it is positive and negative, your function itself, when we go to graph it. So we do a little sign chart. On here, you put your asymptotes and your roots. Your R and your A both go on here. R and your A go on your sign chart. So I'm here at -4, end at -2. And then I do my sign thing, right? If I plug in a -5, that's going to give me negative over what? Negative? You agree with that? So negative over negative gives me positive. If I plug in a -3, what am I getting? Positive over negative. I should have put that over. And then, so that's negative. And then negative, and if I put in a 0, I'm going to get positive over positive, so it's positive. So that tells me what's happening on my graph. It's not an inequality, so I'm not really shading anything because I'm not looking for just one or the other, but I do know where the function is happening. And if there's not an even exponent here, it's not going to cross through. I mean, it has to cross through, I'm sorry. It has to cross through, duh. So it's positive up here, right? My graph is up here, and then it's down here, and then it's up here because of the positive and negative. And this is where my asymptote is, and that's why I know my end behavior is going to have to look something like that. Does that make sense to you? Because it has to go opposite, because they don't have togetherness. Okay? And we'll look more at this. We're going to do lots of examples of graphing them and what all we need to find. But after you do all the PPD Ratey stuff, then you've got to go in and also do your sign chart so that you know where it's doing the different things without making a T-chart of a bunch of points. We're not going to go find a bazillion points at any time. Okay? We good? Any questions? Awesome. All right, good. I was hoping I'd at least get through that. Oh, perfect timing. And then, yeah, we'll do more examples. You don't have any